Okay. So, last time we left off on this, keep in mind that I am never going to be able to do a comprehensive, this is everything you could possibly do with spectroscopy, right? Yeah. So these are all tools. You can combine them. You just have to research and understand what you're doing. Okay? All right. This right here is that mixing coil, by the way, if you're curious. Notice that you increase the surface area and time it can mix by wrapping it. See that? Yeah. And you'll see this coils always look like this when you draw them. They just do these squiggles. Okay? And the coils are always much tighter packed, right? Because you don't need a space between them to tell the difference. All right. This right here is the time and your injection, okay? And so what you'll see is that the detector response is going to peak a little bit after an injection. Essentially, that's how long it takes to pass through, right? And then it's going to trail off as it fades.
So is that inside the coil or at the very end of the coil?
This is at the detector. So your detector is always going to be at one spot in this coil. See that? So your detector's at one place in the coil right here. So you inject it, it goes through the mixing coil, which will cause it to spread and mix. And that doesn't take a huge amount of time because it has a decent flow speed. You wouldn't want this to take forever, right? And the big thing you need to keep in mind here is that essentially you're going to get that first wave, which is your injection wave, and then you'll get a tail. Okay, and that's that balloon. As it spreads out, that sideways motion is not forward motion, right? And so that's going to take a little longer. Okay, but it drops off pretty fast. And then this is the stuff that would have bounced off the walls essentially. And then you get nothing, right? Okay, so figure 1912 actually shows the analysis for traces of herbicide acetochlor in food. And so here's acetochlor, by the way. This would actually be its hydrolysis product here, if you're curious. So your carrier stream is going to contain a diazonium salt. You know diazonium, right? This is an azide group, and so that's diazonium. This is the reagent that would react with the hydrolysis product of the herbicide right here. Okay, so this is going to give us a colored product. That's why we're doing all this reactions, is to get a colored product so that we can monitoring it using visible light spectroscopy, right? This would be much, much less accurate if you had to do something like Raman, right? Or infrared, because there's just a lot more complexity to the peaks. And so you'll see that in like industrial scale, a lot of the amount of something is measured in visible light spectroscopy because the peaks are much more independent. You have a lot less complexity. Okay. You can do it in infrared, you can do it Raman, but you really have to understand what you're doing, and it is typically a much more complex setup. Okay, to do it, like it takes a lot more spectroscopy chops to be able to do it, and you have to really set your situations up to get very nice defined peaks. Okay. Anyway, so this gives us a visible color. This is the colored product right here, and this is actually an azo dye, which you may have heard of before. I think some of the indicators are azo dyes, if I remember correctly. In fact, I'm pretty sure one is named after azo, that you from your old indicator chapter. So that's that. And that's literally this connected to this, right? See that? And you may remember those reactions. Remember where they attack, meta, para. Yeah. But we don't really care about the reaction so much. We just care about, this is what we get. Okay, so the figure 1913 here shows the dispersion and reaction of the sample after it's been injected into your carrier stream. Remember, you're going to inject it. It's going to then mix with your carrier stream, which is going to have the reactants in it, okay? It's then going to mix along that long tail pipe, and then it'll flow into a straight portion, which will then be your cell, right? Whoops. Notice there's a straight, see how this comes down on here? There's like the straight portion. That's why you have that straight portion. That's your cell. Okay? Okay, so if there were no reagent, the sample would just begin to spread out, disperse as it travels downstream. So you would get your injection. If there's no reagent, it's just going to spread out, and you'll get that, and it won't show up at that wavelength, would it? Because that doesn't absorb about that 400 nanometers. You need reagent in there to react, okay? Again, remember that we have done this hydrolysis first. This is what we're injecting, okay? Those are the conditions to do the hydrolysis, by the way. We're injecting this then, because this is going to react with that in the correct position to give us this product. It will react very purely, and it will hold up on those conditions we're looking for here.
So that one's like already
In your carrier stream, yeah. So this is going to be in here, passing through. This is part of that carrier stream. Does that make sense? Yeah, that's why I was stressing that, because it's not always obvious. Yeah.
So is that reaction is done first to the herbicide,
Mm-hmm.
and then you get the hydrolysis product, and that's what you inject?
Yep, this is the injection sample. This would not work well as something you would react and then inject. Like the HCl is problematic in of itself because it tends to corrode systems. But 100 degrees Celsius, it's very difficult to maintain 100 degrees Celsius without deviation. And any temperature deviations would cause the optical properties to change, right? So, in fact, there was a setup. If you were going to do this, by the way, this temperature, maintain a constant temperature, what you actually do is you put a heating element just before along your entire pathway. You ever seen those pipe wrap heating elements? Very similar. So you have like a heating element that wraps your system, and then you put a thermal sheath on it. And then you'd put the temperature detector on the bottom right after your cell, like immediately right adjoined. And then what would happen is the thermal would automatically vary the temperature coming into there. But it's actually pretty hard to maintain 100 degrees Celsius. Like it's much easier to maintain like liquid nitrogen level temperatures than it is 100 degrees Celsius. But you can do it. It's just not the easiest thing in the world.
So it's more you do the reaction outside of it, and you get product to put it in, or
So yeah, so you do this reaction, you'd get this product, then you would inject that. This is actually the injection right here. So this would be what happens after you inject it along that mixing tube. And that's why you have mixing going on. It's not just to get it so it blooms out. It's also like having a stir bar in there to mix it so it reacts, right? Yeah. You just can't have a stir bar because it wouldn't flow. Okay. So with no reagent, you would just get dispersion, right? And then it would travel downstream. And so you'd get something that looks like this. And see how that has the dispersion? It has the lean part, which is your direct injection in. And then this part would be the dispersion right here. As it dispersed out, it slowed down. And the sidewall slow downs even more. Then right here is with the reagent. And you can see that here you get in your reaction product. So you're going to have several different zones here. You're going to have the leading and following parts, okay? And those are going to have your reaction products. You'll get the middle zone right here, and this is going to be rich with the unreacted sample. You'll have a low concentration of the reacted part. Because if you look at this, where is the mixing actually occurring? The front and back, right? In the middle, it's like having like a bullet or something passing through, right? You have a lot of your reactant, no reagent, right? So you got a lot of your sample, but no reagent. And it can't get to the reagent to react, can it? You have to consume this stuff first and this stuff. Okay. Yeah, this actually doesn't maintain a static shape, by the way, in case you're wondering.
Yeah.
Like this rolls along.
Yeah. It's just like the middle of it is going to be like surrounded by the rest of
Yeah, that's the only part that doesn't easily exchange is the middle portion here. The other parts actually, this is not exactly, I mean, it's accurate, but it's difficult to see, is remember that these molecules will actually be rolling along the walls and exchanging out. And that's why you get this sort of shape here. And this has a bunch of reacted part because this is flowing through, right? This is actually the stuff that was up here and rolled along the edges, in case you're wondering. Okay. But still, you'd also get like a sheath of reacted media right here along the sides. Does that make sense? Okay. Yeah, you get like a little tube of reacted stuff, right? Yeah, like a little cone almost. Okay, so you have your radical direction and your axial direction here. Does that pretty much make sense to you? You have any questions? Okay, so when you talk about liquid flows, there's something called a laminar flow. And this occurs when your liquid flows relatively slowly through a narrow column. The friction with the walls of the tube slows the flow to 0 at the walls. So you actually don't have flow at the walls. It ends up getting bumped and picked up later, but at the walls, you don't have flowing liquid. Okay? So the flow at the center of the channel is actually twice as fast as the average flow of the entire tube. So between the center and the walls of the tube, there's going to be a parabolic velocity profile. And that's what creates this shape here. That's the parabolic velocity profile, right? Okay. So the liquid at the walls will mix with the bulk through radial diffusion. So radial direction, see how it's like that? Yeah. So that's what's causing the mixing at the walls, is radial diffusion, okay? So you narrow your tube, the faster the radial mixing. So if you have a very large tube, you get a very slow radial diffusion, right? So it takes a long time to go from the middle to the edges. If you have a much smaller tube, that takes a lot less time, doesn't it? So with a typical tube diameter of 0.5 to 0.75 millimeters, that is not big, is it? No. I mean, it's not like you can't see this. You can very easily see this, right? But it's a tiny tube. Diffusion of the liquid away from the walls is significant in a few seconds. So what essentially happens here is things roll off onto the walls, they get stuck there, and they diffuse back in, okay? And that's why you get this bloom in the back, actually. It's not that the stuff in the back is reacting, right? Because they're all flowing together. So there maybe there's a little bit. Yeah, it's the walls is diffusing back, right? If you have a very large tube, that will be very slow. If you have a narrow tube, it's going to be much faster, right? In correlation with your flow speed. So in figure 19.2, the bulk of the path between the injection and detection is a helical mixing coil. You remember the helical mixing coil. By the way, that's the same thing that you would see in like a mad scientist lab thing. That's actually a helical mixing coil. I don't see them as much anymore because electronic mixers are a thing now. And so, you know, they're only used in specific cases now because they're very expensive. Like helical mixing coils made of glass are extremely expensive compared to other stuff, glassware. And double layer glass, like you saw in your like precipitation setups. Remember that? The condensers? Those things are ridiculously expensive. Like we had to get a part of a column replaced once, only about maybe a foot of glass. It was like a $5,000 thing. That was just stupid expensive. All right. So the curvature and sharp bends in the flow path create turbulence. This turbulence is going to promote that mixing. Basically, it's going to cause things to bounce and swipe the sidewalls, right? So it causes them to get hit back into the pathway, and it promotes that mixing. The reaction with the reagent in the carrier stream occurs from the leading and trailing edges of the sample zone. Mixing is incomplete and equilibrium is not achieved. Essentially, if you can achieve equilibrium, this thing is going to take far too long. That would be no flow rate, I guess. So the key to precision is the repeatability of the flow injection. If you have different flow injections every time, you'll get different amounts of mixing every time, won't you? Okay? And so as long as your flow rate is repeatable, then when you do your standards, it will match that concentrations of your standards, won't it? Okay? But if your flow rate changes, what happens? You would get different amounts of mixing, right? And so even if all of your standards were good, if your flow rate changes and your injection changes, and that mixing changes, that means you would have no reproducibility of results, would you? Yeah. And you'll put in a systematic error once you change your flow rate, assuming that it's a permanent change. If it's not a permanent change, then it would be a random error. Like let's say you took an injection needle and you just had a plastic tube and you were injecting it by hand each time, and you get different angles each time, you'd have random error every time, wouldn't you? It'd be impossible to get a systematic setup, right? Because your hand would change every time. But if you have a tube coming off of it and you inject it into that tube first, and then it loads on, you can get reproducible results, right? So these setups have to be very, very well set up, which is why we don't do them in live. I mean, you have to set it up, and then you have to have it stay the same way for pretty much ever, right? So it's systematic. Obviously, that would not work in a limited space lab like ours. Yeah. So reproducible conditions provide a reproducible result. You need to have your sample volume, your reaction rate, and temperature all need to be reproducible. You need to keep those consistent. The detector has a Z-shaped liquid path. You'll remember that, right? See the Z? The common cells will have a path length of 10 millimeters with a volume of 60 microliters. The injected sample volumes are typically tens of microliters, because remember that we usually keep the tubing very thin, right? And so that keeps a nice consistency for that concentration, that can mix well. It doesn't have a huge ton of diffusion, right? So we can keep a decent flow rate. Peak height is commonly taken as the analytical signal. Okay. So sequential injection is distinguished from flow injection by flow programming and flow reversal under computer control. These setups are very nice because they're very good for computer control of those systems. Specifically because there's a lot of pumps now that are extremely accurate under computer guidance, okay? You know those soda systems where they automatically inject the parts of it and make you the soda you want? Okay, that was actually invented by a guy that invented the, what the hell was that called? Segway, I think? It's the two-wheel thing that, yeah, before the hoverboards. You know what I'm talking about, right? They were kind of derpy. Anyways, that guy actually is the one that invented precision pumps that could pump like medicine dosages for a baby, that sort of thing. And that's actually what he originally invented, where he got his money. And then he blew a bunch of it on Segway, and then he became rich again from those soda machines. Anyways, he's kind of a character, by the way. If you ever watch his interview, he has his house, his entire entry is a giant steam engine from one of those paddle boats. Yeah. So like his whole entryway is always moving. And he's always like working on it. It's something, man. Anyways, precision pumps can actually do very well in these systems. Shockingly well, like better than micropipettes. Not as good as scaling it up, but then you'll have to use a lot more sample, don't you? So these can use a small amount of sample and do surprisingly well. The flow is not continuous in sequential injection. Small volumes of reagents are required and less waste is generated this way. This is also called lab on a valve, which is cute, right? Lab on a valve, just, and you're good. Okay, so this is it right here. So this is a peristatic pump, and these are these precision pumps we were talking about that take out, specific amounts of each one, okay? And you can program to do it. So you'll have a seawater or water sample right here. This is going to come in with reagent 1 and reagent 2. Notice that this is going to be your injection valve right here. So you'll put in standards here, etc. Okay? This one has a thermostated reaction coil, which is what I was talking about before. Essentially, it's like a tube that's kept at a constant temperature, and you'd have a computer monitoring that temperature and adjusting it all the time. Or the other way you can do it is like you can do boiling water and pipe it in and let it come back out. So you'd have steam circulating in here. That'd give you a 100-degree one, though. 65, you would have to usually like have a computer-controlled heating coil sort of thing. Yeah. Anyways, so you're going to get your reaction. It's going to happen at 65 degrees Celsius here. It's going to go on. And then you're going to have your fluorescence detector cell right here. And you see that's the cell right there. So it's going to flow in here. You'll have the excitation come in through here. And remember that fluorescence, you do it at 90 degrees, right? And so you have something like a fiber optic cable normally that would come off here, and that would be your emission out. Okay? You detect it down at the detector. By the way, one of the reasons you always want to use like fiber optic cables and stuff is precision machinery and flow setups like this typically do not match well if you just have them open exposed to each other. Like imagine what happens when you have a leak. And then your precision machinery gets sprayed with shit, right? You imagine? That'd be such a disaster, right? Having to open it up, clean everything out, put it back together, then, you know, you'd have to retest the whole thing and tweak every single thing within. Some of these setups are micrometer changes. It would be an absolute unmitigated disaster, right? Yeah. So typically the detector setup, the instrumentation setups are sealed. And then you have fiber optics coming into this, okay, to transport the light. Those are the better setups I've seen. You can have it the other way, but they are much less accurate because they cannot be anywhere near as precise, right? Anyways, so the central feature is a 6-way valve. 2, 3, 4, and 5 are used in figure 1916 here. Port 5 right here is connected to port C. See that? So port 5 here is actually where you get your sample coming in. And that's your port C right here. Okay? Okay. So liquid samples are actually brought to port 5 by an auxiliary, excuse me, peristaltic pump. So you got your pump working here to move things in port 5. Yeah. So notice here's your reagents, ports 3 and 4. This is a 6-way valve. 6 is not actually being used though, okay? And then L1 is not being used either. So you have 2 of them that aren't being used right now. This has your carrier buffer. This is pretty common if you have anything like proteins, that sort of stuff, because a lot of them will change with pHs, right? As you've experienced. This right here would be your syringe pump. Notice this is what's called a 3-way valve. 3-way because it has 3 directions off it, right? Then this is your temperature-controlled holding coil. Notice it's a mixing coil to get these mixed, but it doesn't always have a flow through it, okay? Anyways, do you have any questions about this? No? Okay. This literally is just 6 directions off that valve, right? You need an auxiliary peristaltic pump, by the way, because when you have more directions coming off a valve, it's going to weaken your flow rate, right? So this keeps that flow rate reasonable. So the rotation of the valve by computer control can connect any one of the ports to C, right here. There's going to be a step motor controlled syringe pump, which is this right here. This is going to move precise volumes of liquid forward or backward under computer control. And this can go both ways, by the way. You can inject or you can remove, okay? So this shows how a reaction of a sample with one reagent could be conducted. So here we have that 6-way valve here. See that? Okay. So in here we have the holding coil and the carrier right here, okay? So you inject your sample into here, okay? You're then going to inject your reagent. And remember, this is hooked up to both of those, right? So it's going to inject sample, then reagent, okay? Okay, so now it goes off to that mixing holding coil, right? And this is why it's referred to as a holding coil, because what you'll get is you'll inject both of these, and then you're going to hold those for a bit, okay? And then what you're going to do is reverse flow. And once you reverse flow, this six-way valve is going to move to the detector now, okay? And that's going to let this back through to the detector. And notice you'll have product in between these two because those are the only places this is, right? Cool, huh? Isn't that beautiful? And this system can be completely automated, okay? You can literally set this up like in a Coca-Cola factory. It's attached to the main tank or mixing tank, and it literally does this where it takes sample from here, puts something in, and does this entire experiment like 100 times a day, okay? Every single batch you do this. Or you could do this for a, you know, a pesticide or a herbicide or whatever, right? And it can be fully automated. In fact, you'll probably have a spectroscopist on staff, but their job is to figure out when this fucks up and fix things, right? And then they would do some standards and quality control every now and then, make sure this is running correctly, right? But this system can be fully automated, so it literally tells you yes, no sort of things. You have like a range of numbers, and whoever's working on a day is going, well, it's within that range. We're still okay. And typically you'd have like a staff that would come in and work like small shifts, or you'd have the samples sent off, and you would have them quality control the system. Anyways, this is what this looks like right here. Okay, notice they can pretty much be fully contained, automated. There is not, like, it's a magic box that you put stuff in, right? You're not sitting there, like, doing anything manually, okay? These things can be smaller than laptops. The smallest one I've ever seen, and that's probably not the smallest that exists, is, actually, no, that's wrong. I have seen the smallest one that probably exists right now. I've seen one the size of a computer chip. Like an inch or so on each direction. And you could probably theoretically make slightly smaller than that, but not much. Because at that point, you're looking at like a few molecules moving. That's pretty small. And that one was what was that for? It was for a disease. I think it was HIV. I think it detected HIV. I don't know if they ever actually released that though. Huh. Anyways, you can make very tiny ones. But most of them are more like a laptop setup size, right? Because once you get too small, it starts getting its own challenges. Like you start losing the damn things. And you can't work on them anymore, right? So if they break, they're better just to replace it. So immunoassays. Immunoassays are going to employ antibodies to detect the analyte. The enzyme-linked immunosorbent assay, ELISA, is right here. So we have antibodies that are linked to a polymer support. See that okay? And these can be a wide variety of things. They could be in a tube setup. They can also be strands, and they can also be beads. Typically, I've seen them as beads. Those are the most common ones I've seen for purchase. But yes, you can have a wide variety of what this polymer shape is. It's just a polymer, right? So you can cast it like plastic. You could make little war soldiers and play video games with, or tabletop games with them, right? It's a polymer. But you don't. That would be so expensive and so stupid. God, I hope nobody ever does that. Anyways, you would add a sample containing analyte. You would then wash to remove that on-bound molecules. So you'd add your sample, and then you'd wash that sample through for anything that's on-bound. Okay? So this would be the analyte protein that's bound to the antibody. By the way, yes, this can be like an antibody test sort of thing, where you're looking for the spike protein or whatever. But it also can be a wide range of things now. They figured out how to custom make antibodies. Okay? So, like, I've seen tests for this that are using like antibodies to detect sugars and stuff. It's crazy. This has really bloomed in the last like 10 years. So you'd add enzyme labeled antibody 2 to this. Then you'd wash to remove the unbound antibody. Okay, so now you've put your analyte on your antibodies that are bound to the polymer, right? So the next thing you do is you add the what you think the antibody, what you think contains the antibody that binds that analyte. So you've bound the spike protein from COVID, right? Now you take the serum sample from a person, you put it in there. That's going to have the antibodies that function on there bind that spike protein. Does that make sense? Okay. And so now you've gotten that antibody that binds the spike protein purified, haven't you? And you've gotten it, you can take it back off and determine, what the hell it is. And then you can make, vaccines that target that. Okay? Does that kind of make some sense? Okay. Okay. So antibody 1 here is with a polymer bound one. That's specific for the analyte of interest. It needs to be bound to a polymeric support so it doesn't get washed through. This needs to be, remember your mobile and stationary phases in your separations? That's all this is, right? We're setting up a stationary phase, okay, that can bind it. Did you guys ever do any resin beads doing like ions or stuff, anything in Gen Chem? Yeah, you probably didn't. But you did do like TLC plates and stuff, so you know the general concept. Yeah. There's a really good one that's an optional lab that sometimes we do. But it's hard to get time to do everything. So the analyte is going to be incubated with the polymer-bound antibody to form complexes. That's this step 2 here. And then the fraction of the antibody sites that bind analyte is proportional to the concentration of the analyte unknown. The surface will then be washed to remove unbound substances and leave our analyte. You gotta be careful with your washes. If you're not careful with your washes and you, acid releases this and you let it be too acidic, you can have nothing, okay? Seen that happen more than I would like to admit. So in steps 3 and 4 here, that's down here, the antibody antigen complex is then treated with the antibody 2, which recognizes a different region on the analyte. This is one thing that's a limiting factor for this. Keep in mind, these are actually binding to binding sites, right? So if they try to bind to the same site, guess what happens? Part of this goes back into the mobile phase, and goodbye. That's done. These can be covalent bonds, by the way. Don't think they're just hydrogen bonds or hydrophobic interactions. So these can be full-on covalent bonds. You can do things like disulfide bridges, that sort of stuff, okay? You can even synthesize analyte abducts. Remember how we were talking about synthesizing a variant of an analyte? You can synthesize something that has an additional group that can bind on this, okay? So there's a lot of options here. I'm just trying to point out some of them so you can broaden. So this antibody has a covalently attached enzyme here, okay? And so this is actually making some sort of covalent attachment. This could be, ester, this bind linkage. This could be a disulfide linkage. So the enzyme can transform a colorless reactant into a colored product or convert a non-fluorescent reactant into a fluorescent product. Actually, the fluorescence one is the most common one I've seen. The colored happens, and they're really convenient when it does happen. And I've seen ones that, you know, are specifically designed for that to happen, or it just happens naturally. But the fluorescent one is very common. Like most proteins are fluorescent in some way or shape or form. So that's very easy for an enzyme to be fluorescent, okay? Which is nice. The hard part is to get it to have a shift that you can actually see that independently, right? So this can catalyze the same reaction many times and amplify your signal. So for example, here we have an enzyme that's bound to this antibody. So we put in a colorless reactant, and this enzyme is a catalyst, right? So it's going to continuously change this colorless reactant to a colored product. And so over time, our signal will actually increase, right? Here we have a non-fluorescent reactant that goes to a fluorescent product. And so you can get the same thing. The higher the analyte unknown concentration, the more enzyme is bound, and the greater the extent of this reaction here. So in this case, we can tell the concentration of our analyte here because of how much this reaction is being amplified, right? So the more of this analyte, the more analyte protein complex, and the faster this reaction will be, right? And this is very much ties into our biochemistry. Remember we were talking about Km and all that? Yeah. Okay, so the sensitivity to less than Ng of analyte. Remember that because this reaction is occurring, you can actually boost your sensitivity to this analyte by just allowing this reaction to occur a bit longer. Because it's an enzyme, right? It's not going to get used up. So this can be incredibly sensitive if you're willing to take the time and effort for it. Okay? Which is nice, right? There's not a lot of analytical techniques that you find that it can be pretty much as sensitive as you damn well please. Okay? But this has a built-in amplification step, right? And so this can pretty much be as sensitive as you want it to be. Okay? The excited state molecules can serve as chemical sensors. A molecule can absorb light. This is a different part, by the way. I switched over to 19.6. Okay, we're done with this. Okay. Yeah, I didn't have a very good switch over, did I? Okay. So this is going to be sensors based on luminescence quenching. And notice the luminescence quenching. So instead of looking at the luminescence, we're looking at it quenching, right? Okay. And this is a very different type of spectroscopy, okay? Like there are different types of spectroscopy. There's luminescence, there's absorption, right? But there's also things that are like degradation and falling down from excited pathways. NMR is a type of degradation where you have an excited state you make and then it falls down over time, right? Okay. So excited state molecules can serve as chemical sensors. A molecule can absorb light or absorb electromagnetic radiation. And so here we see a molecule absorbing some sort of light, right? And this gives us an excited state. And so this rate equals the change of the excited state over the change in time. And just like any other reaction that has that same rate constant times the concentration of your reactant. Remember that rate laws are always stated in terms of reactant, okay? But you can state the rates in terms of change of anything, right? Over change in time. Okay. So this following absorption the excited state can then emit a photon. Remember, this doesn't necessarily have to be the same frequency, right? So your excited state is going to emit a photon, giving you back your ground state product, okay? In this case, this is probably the same deal because we didn't state a different energy level, right? Okay. And, you know, you can do a lot of different things here. You can fall down to a different energy state and target that one. Or you can target the same falling back from the high energy state. Either way will work. They both have advantages. Okay, so excited. This is the emission. So this means for the emission. And this one's for absorption. Okay? And you can see here that, again, you're just, yes, it looks like you're just flipping this, but remember that this one had the light coming in, this one had the light coming out. So it's not the same constant. Okay? You have a different rate of absorption and emissions.
So the rate is still with the excited state. Oh,
This is the rate constant with the excited states. Now that's your reactant.
yeah. I was just wondering about the rate.
Oh, yeah, we're just defining these by the excited state change in both of these, because that's the one we're going to want to look at and measure. You could have defined, like, there exists a rate equals, in this case right here, let's do it for this one real quick. There exists a rate equals D and M with no excited state, but that has a negative in front of it. Okay? And you could have done that. Equals that, then it equals this. They're the same, right? And what that would look at is this would be falling as you absorb photons, right? And this one too. See that this is now negative because this one's falling as it emits, right? But as it emits, it increases the concentration of this end. We just don't care about that. Because we're doing luminescence quenching, right? How fast this quenches its luminescence. So all we care about is the excited state, right? This part has to be defined by the reactant. You can only do rate laws by terms of reactant. You never, ever, ever make a rate law in terms of product. Okay? And that's why that's reactant right here and the reactant here. That's why it's different. Okay. Oh, wow. We really went over, didn't we? Okay, we'll stop here and we'll pick up on that.